Let's just jump right in. In this explainer, we're going on a journey to uncover the invisible physical forces that power, well, almost every single aspect of our modern lives. We're talking about energy that is constantly in motion all around us, transferring power from one place to another, yet completely invisible to the naked eye. Let's dive in, shall we?
So, what do a cell phone, a standard car radio, and a hospital x-ray machine actually have in common? On the surface, they seem completely unrelated, right? I mean, one fits right in your pocket, one blasts music during your commute, and the other literally looks right through your skin. But underneath the hardware, they share a pretty profound connection.
The answer? They all use electromagnetic radiation, or EMR for short. Now, I know that sounds super technical, but at its core, it's really just energy created by the vibrations of electrically charged particles. Because of these rapid vibrations, this energy can travel through space and materials. Engineers just harness different parts of this radiating energy depending on exactly what they want a device to do. When this invisible energy actually moves, it travels as a transverse wave. If we break down the basic anatomy of this wave, the absolute highest point is the peak, or crest. The lowest point down in the dip is the trough. And the distance from that imaginary center line straight up to the peak, that's the amplitude, basically the actual height of the wave itself.
This basic anatomy builds right into one of our absolute most important concepts here, wavelength. This is the specific distance between repeating features of the wave, most easily measured by just going directly from one crest to the very next crest. Some of these waves are incredibly stretched out, while others are packed super tightly together. And this physical distance determines exactly how the wave behaves in our physical world.
Now, here is the crucial piece of the puzzle, the relationship between wavelength and frequency. Frequency is just how many times a wave pattern repeats in a specific time frame. I want you to think of it like a playground teeter-totter. It's a perfect inverse relationship. If a wave has a really long wavelength, it has a low frequency, and therefore low energy. But if you push that teeter-totter the other way, as the wavelength gets shorter, its frequency and energy absolutely skyrocket.
And that brings us to the entire electromagnetic spectrum, our master map of all this energy. Notice how the waves transition. On the far right, you have your long wavelengths and low frequencies. As we move across to the left, the waves get tighter, the frequency increases, and the energy really ramps up. For the rest of this explainer, we're going to ride these waves from right to left, exploring how each unique section actually gets used. Starting on the far right, at the low energy end, we have radio waves. You can think of these as the gentle giants of the electromagnetic world. They have the lowest frequency, but the absolute longest wavelengths. We're talking anywhere from a few millimeters to several kilometers in length. Because of this massively stretched out shape, they're perfect for traveling over huge distances.
So, what does that mean in practice? Well, radio waves are the backbone of our long-distance communication. They carry your AM and FM broadcasts, they're heavily utilized in aviation and weather tracking to keep planes safe, and they literally power the navigation systems that keep our entire modern world connected. Taking one step up the energy ladder, we reach microwaves. Their wavelengths are a bit shorter now, ranging from about 1 meter down to 1 millimeter. As our trusty teeter-totter analogy tells us, because the wavelength has decreased, the frequency and energy have naturally increased. They're still considered low frequency overall, but they definitely pack more of a punch than radio waves.
Obviously, you likely have a device using these in your kitchen right now. Microwave ovens harness these waves to violently oscillate water molecules and heat up your food, but they go way beyond just warming up leftovers. Microwaves are totally crucial for telecommunications, wireless networking, and radar. One quick important note though, because of their higher energy, they can actually cause interference with sensitive medical devices like pacemakers.
Moving even further left on the spectrum, we hit infrared radiation. We're increasing the frequency yet again. These waves are created by the vibration of atoms within molecules, and while you can't see infrared radiation with your eyes, you can absolutely feel it. Infrared is deeply connected to radiant heat. It is literally the energy emitted by very hot bodies. Infrared has some incredibly fascinating applications in our daily lives. Believe it or not, it's the invisible energy your TV remote uses to communicate with your screen. Night vision devices work by capturing this exact heat radiation so we can see in the dark. And in medicine, infrared heat lamps are highly effective at warming up tired, aching muscles and promoting tissue healing.
Next up, we cross into a tiny, very special sliver of the spectrum, visible light. Out of this massive spectrum ranging from kilometers long to microscopic fractions of a millimeter, this is the one and only portion our human biology can naturally detect. Driven by the rapid motion of electrons, the varying frequencies within this band give us all the vibrant colors we see, ordered perfectly from lower energy red all the way through to higher energy violet. Aside from providing basic illumination for our world, visible light is harnessed for photography to capture the world exactly as we perceive it. It's also becoming increasingly vital for high-speed optical communications. Think about fiber optic cables carrying internet data using incredibly rapid pulses of light. It's a real game changer.
All right, now we step past what our eyes can see, moving into the much higher energy territory of ultraviolet, or UV waves. The wavelength here drops way down to between 10 and 400 nanometers. As the frequency shoots up, we mark a really critical transition point. This is where the physical impacts of these waves on the human body become much more intense.
The real-world uses here are highly specialized. Hospitals use UV light to keep operating rooms completely sterile, and forensic investigators use it to spot counterfeit documents. Biologically speaking, small doses actually stimulate vitamin D production in our skin. But overexposure causes painful sunburns and can unfortunately lead to skin cancer. It's a powerful energy that absolutely demands our respect.
Moving up again, we hit X-rays. We are now dealing with incredible frequencies and impossibly tiny wavelengths between 0.01 and 10 nanometers, created by rapid reactions and the deceleration or charged particles. Their energy is so intense that they have tremendous penetrating power, literally passing right through human skin and soft tissue like it's not even there.
This penetrating power makes X-rays a massive asset for medical imaging, letting doctors look directly at our bones without a single surgical incision. They're also totally vital for airport security and detecting microscopic flaws in industrial manufacturing. But with high energy comes high responsibility. These waves can kill healthy cells, which is exactly why the technician always steps completely out of the room when they're taking your X-ray. Finally, we reach the extreme far left of the spectrum, gamma rays. These boast the absolute highest frequency and the shortest wavelengths of them all, less than 0.01 nanometers. These aren't just created by moving electrons. No, these are unleashed by intense nuclear reactions and radioactive disintegration. It is the absolute peak of the energy scale. Now, while you might immediately associate nuclear reactions with destruction, gamma rays actually have incredibly beneficial uses when we harness them correctly. Their immense, pinpoint energy is a cornerstone of modern nuclear medicine. They are used in radiation therapy to precisely target and destroy cancerous cells and to achieve high-level sterilization of critical medical equipment. So looking at this summary, we can see everything we've just covered side by side. You can really see our teeter-totter rule in action, from massive low-frequency radio waves at the very top, down through the visible light we see, all the way down to those microscopic, ultra-high-frequency gamma rays at the bottom. Getting to map the exact ranges makes it so clear just how essential every single part of this spectrum is to human progress. Which brings us to a final thought for this explainer. From the radio playing in your car to the life-saving imaging tools in a hospital, we have actually managed to harness the very vibrations of the universe. So how will our growing mastery of these invisible waves shape the technologies of tomorrow? What crazy new devices are waiting just around the corner, hidden in a frequency we haven't quite figured out how to utilize yet? I'll leave you to ponder that. Keep exploring the invisible world around you.